Yeah, so original title was running solid efficiently, but actually it also, my talk also affect people who run molecules with SEO. Some of the features universal. Just introduce myself. I'm Yelo. I'm working at Argonne National Lab. Yeah, that word doesn't work. Fine. So at a computational science division and also in the leadership computing facility. So I did a lot of work mostly developing QMCPACK. A large chunk is somehow invisible to users. So today my talk will cover two parts. One is a few of the new features I developed in the code. The other is performance improvement. So that's it. So the first one is the size consistency moves that we didn't have in QMCPACK for a while because the scheme from Michele Casula in 2020 with the size consistency scheme, but we didn't have that for many years. But this is an important feature. So let's go through what is T-moves and what size consistent T-moves. With T-moves in DMC diffusion Monte Carlo, it gives you back the variational principle and also improve the stability of the simulation. So without using T-moves, you will see those spikes and your population may easily blow up. But with T-moves, you have more stable calculation. This affects pseudopotential calculation only. If you're doing on all electron, it's irrelevant. So in QMCPACK, we will give you these. In the past, we have no and yes. Now we have two new options, V1 and V3. So the yes, V0 is the 2006 paper from Michele Casula. This scheme is not size consistent, but give you the stability. The V1 is the scheme provided in 2010 paper, which is size consistent, but it's very slow. And we add a new option, V3, which is basically an approximation on V1, but almost retain the same accuracy and runs much faster. So remember that V1 is very slow, but could reproduce. It's exactly the same algorithm as the paper. But V3 is I would recommend to users to use. So V3 has been tested on molecules, light elements, as well as transition metal oxide solids. So we actually didn't find a noticeable difference compared to the V1. So users either doing molecule solids could use this one.
Just one plug I'll put in for the version 3. Relative to the others, I've noticed it really reduces autocorrelation time. About a factor of 2 relative to the other algorithms.
Even compared to V1?
Yes.
So less autocorrelation compared to the more accurate one?
Autocorrelation.
Yeah.
From what I
Side
see.
effect.
It may not generalize, but that's what I've seen. So look for it anyway.
Maybe there's a gotcha because I tweak the code a bit between 3.6 and 3.7. So this 3.7 is the most exact one. And we didn't find any difference compared to V1. But anyway, yeah, if it's a reducing autocorrelation time, it's definitely good to use, yeah. So yeah, this is basically telling you when you do an experiment of water molecule set very far away, then you start to add the number of water molecules, and you compute the energy per molecule. You notice without using a size consistent scheme, you will see the energy is actually growing. But with a size consistent scheme, it's flat. And it also affects your judgment of making a reasonable time step. We can't always do, I would say a lot of cases, especially heavy ones, you don't even get a chance to do time step extrapolation. So with a size consistent scheme that actually you can use, just do a fixed time step, because you assume the time step error would cancel out between different runs. But there's no bias from the T-move schemes you are using. So the other thing is, Kaihan yesterday mentioned is the hybrid orbital representation. Basically, it's used for single particle orbitals. It's not your whole wave function, but just the single particle orbitals. So in QMCPACK, we used to use molecular people like LCAO and solid people like B-splines. B-splines is specific for QMC, which is similar to the plane waves in DFT land. It's easy to control, but we made a choice that you have a n-square computing, but unfortunately you have still n-cube storage. But for the not n-cube storage, it's still n-square storage, but with a much larger prefactor with the B-spline. That's why you often hear people complaining, I'm using B-splines fast, but I run out of memory. I can't keep on. So this is really bad. It makes you stop. You can't do anything beyond that. So we are really trying to develop a scheme and solve this situation. The scheme originally development in QMCPACK in around 2010, but that scheme has a bit other complications. So I decided to make a more clean implementation, give you high efficiency and as little hassle as possible. So with this scheme, to save memory, the logic is very simple. Think about this is your wave function. Originally, it's being put on a grid. So there are atomic centers. That's why you see a bit of color difference, because the wave function change values dramatically around the nucleus. Instead of directly using a grid, the best way is actually represent them with LCAOs, we all know. So it's kind of APW scheme. And to have better numeric property, we also introduced a B region. That's just a buffer region smoothed out between the atomic region and the B-spline region. So in this way, that we are able to dramatically nail down the memory usage and make it fit in those high bandwidth memories on modern architectures. So accuracy, yes, we really care about accuracy. So give you a bit freedom, feelings of the accuracy. So when you do B-spline, when I apply different mesh factor, basically I'm adjusting the spacing of the grid. If you just use a regular regular grid, you notice that when you're coursing the grid, the accuracy around the orbital value around the core changed dramatically compared to the reference that's the plane wave. So with our new scheme, actually, you have the value right on top of it, even that you can, even regardless what mesh factor you use, because it's around the core, so it's always accurately captured. So that's reflected on your QMC calculation as variance. So you might notice nothing on energy, but you will notice the variance reduce a lot. So I know people doesn't do QMC, usually doesn't have a concept of variance. They just say, oh, my energy is good. But you really need to look at your variance. That's also very relevant to the quality of your calculation and also to the cost of your calculation. So to use this feature I made it rather simple. So the current route is from quantum espresso. So you run your usual quantum espresso calculation. There's no action item there. Then when you run QMCPACK, so you need to supply these input keywords. So it comes on two parts. One is to turn on a feature with a bit of tweaking parameters. The red ones you must provide. So like this case, you just choose the other defaults. You choose this one, turn it on. And on the other side is for atoms, you need to describe your A region, B regions. So you provide the cutoff distance, as well as a bit how high the angular momentum, the atomic region basis that you want to set. So after doing this, inside QMCPACK, we will convert your plane waves into those radial functions. And this being parallelized over MPI and OPENP, so it's super efficient. And most people, if you don't do like 200 gigabytes of wave function, you even don't notice it. So this is way better than the old scheme we had in QMCPACK. So with this one, it's very easy to use. Those parameters is a bit subtle. You have to tweak it. You have to do parameter scan. So there's support in the Nexus. Actually, you can ask Nexus to do the scan for you. Then you make a decision what to go beyond that. So a bit of feeling for the accuracy. So when you're using a regular grid, even with a very high, with a very high mesh factor, you will see this is the reference I put. But if you start to force the grid, and you notice that when you're doing DMC calculation for a large time step, you will see a larger time step error. So with hybrid representation, you will find it's right on top of the very dense grid. So you save memory, but your accuracy is super high because you really have an accurate description of the core region. And the other side is the energy. So if you look at the energy and you start to coarse down the mesh factor, you will find that with hybrid representation, it's super accurate. It stays mostly on top of the reference line. But with the regular grid, you easily diverge the energy and also diverge the variance. Variance goes up very quickly. So really important to use these features. So now I'm switching to the performance improvement inside QMCPACK. So this is a figure I drew for the ECP report. And over the 2 or 3 years, it looks like we were mostly improving the CPU code, but this is a lot of preparation forward for the future architectures. So we want to settle down a lot of internal things and make the code faster. That better facilitating us making decisions for the future. So just give you a feeling. On the CPU side, over the 2 years, we basically have 3x speed up, even on BlueGeneQ, which is a machine at the starting point already out of date. There's no new software, but we just sharpen the code, the algorithm, we achieve this figure. So the last develop, you can think it as 3.7, the latest release you get. So we build a lot of new features, like now on the CPU code, you are allowed to use mixed precision, basically. All the wave function calculation mostly comes to the single precision. So that could save memory and save computation as well. And the technique we used to implement this is portable. We mostly relied on the OPENP. So we've tested it works on Intel, AMD, IBM, ARM, all the CPUs basically. And I showed the BlueGeneQ result, but if you have Xeon 5, actually most people have that one, and on their local environment, you will gain way more speed up. So one of the reasons is we introduced this structure of array transformation. It sounds like a data layout change, but it's actually most of algorithmic change that helps you. So it's been introduced in 3.2, and now it's 3.7. So if you hit any issues with it, let us know as soon as possible. I know that we didn't change to default. We were conservative, but I think we really need to give it to users and force users to use it and give us feedback. So it's basically this technique leverages the CPU SIMD hardware and use a portable scheme. The algorithm part is this, actually. So if you know the AOS implementation of Jastrow factors, they have a horrible memory footprint. It's basically n squared n cubed memory. And when you run a large problem, it dominates all your memory. So after changing the algorithm down to n, the memory on the Jastrow just gone. Because of all the algorithm change and SIMD implementation, the cost of Jastrow actually also goes down. And people used to say that the Jastrow 3-body is very heavy. No, it's no more the case. And Jastrow, you can even choose a very large cutoff to include more pairs or triplets of the particles and to gain your accuracy and efficiency. So these are tested on very small systems by looking at throughput and looking at the memory usage. So for the throughput, you switch on the mixed precision, you gain a bit, then you change the algorithms and you gain a lot. So like this small system, you get factor of, I don't know, like 3. Yeah, you get a factor of 6 even there with the larger systems. So for the memory, you notice before we were, on KNL, we have this 16 gigabyte high bandwidth memory. So starting, let's take the bigger problem. It's already beyond the high bandwidth memory, means your performance is penalized by the DDR speed. But changing the mixed precision and also use better algorithm, we just go below the envelope. And we always land the calculation in the fastest memory. So this is super helpful. So this is a feature actually invisible to most of the users because we turn it on by default since there's no hassle to users. So the thing we did is to introduce a memory pool for all of the memory used for each worker in the wave function. This actually dominates the memory usage in QMCPACK, the per worker or per thread memory. So by using this pool, actually we are able to not copy the memory between the buffer, the staged area for communication and the computation area. So it's only one pool. So this is very efficient, help us saving memory and get rid of data movement. And also that the data movement across nodes has been optimized. So originally QMCPACK has a blocking send receive mechanism to exchange workers. So in DMC algorithm, your worker is being given birth to and being killed. Then at a certain point, you need to do load balance. You have to shuffle the worker around different nodes. So in the past, the blocking send receive implementation caused the serialization. And actually, all the nodes are serialized waiting for the communication, which is really bad. And now we get rid of the packing, unpacking, and we also get rid of the waiting. So all the communication becomes non-blocking. And we've seen this speed up like a factor of 2 on Titan when we run the whole machine, as well as Theta at LCF. So the 3.6, I implement the new things called the delay update algorithm in the DMC for all the drivers, DMC, DMC, RMC, they are all supported. So the idea is in QMC algorithm, when you do single particle move, when you accept a move, you have to update the whole inverse matrix. So it's but to update that, the algorithm was using Sherman-Morrison rank 1 update, which is very, very computational inefficient. So we changed the scheme into a delayed update algorithm, use a more jam matrix multiplication based blast calls. So using this Sherman-Morrison Woodbury formula. So this significantly helped the performance of QMCPACK, mostly for the large problems. So here is you do a scan. So the one is the default to the current, there's no delayed update implementation. Then you start to increase the number of delays. Say when I don't accept the move right away, I wait like 16 or 32 acceptance, then I do an accept. So the performance gain, this is a whole DMC calculation performance gain. You might notice for small problems, so if you're running like the 300, 700 electrons, actually you just gain like 20-30%. But if you start to go a bit larger, 1,151,000 electron or 1,500 electron, you start to get a factor of 3 speed of your whole DMC calculation. It's not just for a function, it's a whole code speed up. So definitely for people who's running big simulations, need to consider turn on this feature. And my suggestion is you just start with 32 and scan a bit. Because for small problems, no matter you put, it doesn't really matter that much. For large ones, so this is a good starting. So you only need to add this in your input line. In your Slater determinant delay rank, you put 32 and down.
So yeah, the transition is somewhere around 1,000 electrons that people should really switch this on?
No, even for small ones, you notice a bit like 20% of the overall run. So people may not care that small amount. Like this is at 700. So I would recommend people starting from 500. You need to pay attention to this. Yeah. So a bit more. People like me, ambitious, like to run really big systems. So maybe starting from 3,000 electrons. So we find that the old scheme we use for QMCPACK have a single core per worker, or one worker per core. It really becomes our limit to make the run faster, to reach the time to solution faster. So I implement this using nested OpenMP that you will have a second level of thread, then serving a single worker calculation. So by using this, depends on the problem size. When you need this feature, actually your problem must be large enough. And this size, 256 atom, I consider the small problem for using this feature. So you just add a bit threads. So I'm giving an example. The K9 node is fully populated. Then I reduce the amount of workers, increase the number of reduce the amount of workers, then have multiple cores serving a single worker. So it's like 2, 4, 8 cores serving each worker. The speed up is not the throughput, but just the time for advancing a worker. So you will get those speed up. So it's very helpful on machines that you don't care that much about efficiency, then you really need a time to solution and go for that. And also to reduce your memory need.
Sorry, I'm just still not understanding correctly, or at least I'm pretending that I'm not understanding that, so you just explain it slightly better. So when you reduce the number of workers, let's say I had 1 worker per thread. So if I were to use 64 threads, I would get the linear, that's my baseline.
Yeah.
But now if I divide it by 8, technically I should have had 8 times slowdown, right?
No, it's not a throughput.
Yeah. But
So if you have 1 core working on 1 worker, your time is 1. And if you have 8 core working on 1 worker, your linear behavior will get 8 times speed up. But because it's not perfect, you will reduce the efficiency.
Yes. But that loss is estimated to how much? We're losing about how much at 8 like?
It's 50% loss at 8 threads. You don't need to go there for this problem size. Yeah.
So just as a comment, this is probably most useful when you're trying to reduce the time spent in equilibration, right? Where you really just need walkers to advance rapidly forward in state space and exit that period, because you're going to spend an awful lot of your computer time on a large system on a wide kernel machine in equilibration.
Yeah. You can do this at equilibration time. Then in QMCPACK, there's a mechanism will duplicate the amount of worker if your target worker current population is a factor of 2 difference. We just boost it for you.
So yeah, let me also just add another example maybe that would help understand this. So let's say, for example, I have a giant system and it takes huge amounts of time just to make 1 step. Mm-hmm. This is definitely the case where, and of course to have some relevant statistics, I need at least 100 steps or 100 blocks to be able to be relevant. Yeah. Even if I have 10 blocks but on multiple walkers, it's still not enough because I need to have 200 blocks. This is the type of cases where having more walkers, more threads working on a walker will make the time for my step go faster.
Yeah.
Right? Even if I at the end, but at least my statistics will be more relevant.
Yeah. The other scenario is you just ran out of memory. You don't want to idle cores. You have to consider the extra cores as free.
And it's not implemented in molecular systems, but I have very large molecules where 1 step takes forever for multi-determinants, for example.
It's not implemented on multi-determinant yet.
But once it is, this is typically the case where I can guarantee having 100 blocks to be able to do correct steps.
Yeah. There's a significant need, and we hope people could have innovations and improve that in the multi-determinant. Yeah.
I just used the example.
Thanks a lot.
The worst case.
We often run into worst cases when we go big. I have to be careful of the time. So this is just a simple example for this simple little tool we added to QMCPACK to help you investigate problems if you start running on a new machine. This is basically to check that your thread and the affinity, MPI rank and thread affinity was placed rightly on the hardware you're running. Because unfortunately, we don't have only one kind of processors. We have N vendors. Even one vendor will produce two types of processors. So the way to control them is not in one way. Then you have to, especially on a new machine you've never run before, you have to be careful. So this tool basically prints that the MPI rank and threads, how they bind to the cores. These are logical cores, not the physical cores. You know, nowadays, vendors have, each core have hyperthreads. Then when you do the LSCP, you will get like 2 or 4 cores. And you know that if you, on a 16 physical core machine with 32 threads, but if you just bound 16 workers, and 2 of them sitting on the same core, but 2 different hyperthreads, you are penalized. Your performance goes bad. So then you need to investigate why it happens, and you need to set up a bit environment variables, make sure they land into the right cores you want. So QMCPACK Affinity is to help you to do this. It supports the rank, MPI, and also 2-level OPENMP. So when you use the nested OPENMPs, you have to pay attention to the second level. If you don't use it, pay attention to the first level, and make sure these cores are just bind to the right ones you need. So there are some small, I call it small optimizations that in pseudopotential evaluations, we introduce a new algorithm that is called the batched evaluation of all the quadrilateral points. So this is mostly to improve the performance on the hardware, that to bypass certain inefficiency in the runtime or overhead. So you may consider using this feature for your calculations to gain like 10 or 20% of efficiency. And for hybrid to orbital representation, there's special optimization for this particular feature, because for when you do a quadrilateral point on the sphere, radial functions you only need to evaluate once. You don't need to do multiple times. So you save computation there. Okay, that's it. This is just a miscellaneous thing that I provide a patch for QMC for PW to QMCPACK. Basically, it's directly lived on the GitHub. So if you really urgent need to pull something, you can go there. And there's history, so you can see all the changes. There are some future development, as Paul mentioned. We are going towards one code path, and we've made a prototype of new schemes. I think we are confident we have some ways to go there. In the past, that all the CPU side change of algorithms really helped us to get prepared for the change for reaching one code path goal and future architectures, not just NVIDIA. I mean, all the vendors. Yeah, our goal is to have efficient execution for small, medium, large problems. Although at the moment, I only did the large problems, so hopefully soon we will help you to get the small and medium problems run efficiently. We also hope to add more observables. I really feel like we need features to help users. And as Fernando mentioned, yeah, we did a terrible job writing documentation. I feel sorry. So I made my effort to delete more useless APIs, delete more useless functions, make it more clear. Every API is documented. Then we will create a developer manual for specific pieces that people can land on easily. Yeah, that's it.
Any questions for Ye on any of those features?
Yeah, about the implementation, you said that you changed from arrays of structures to structures of arrays. You can choose now whether to compile one or the other or run one or the other.
So,
repeat the question.
So, Alfredo was asking that we changed the data layout AOS to SOA, that is every piece supporting that, or it's a hard compilation option? Yeah. So it depends. For certain data, share the data object between, like the particle set, particle positions are shared by all the wave function pieces. So then all the wave function pieces, has dedicated, it's either AOS or SOA. But the particle side, we currently, as a temporal solution, is you have both kept.
Yeah.
But
it's the hard compile option,
yeah.
and there isn't transitions between them. Hence, what I mentioned over lunch, right? We're getting away from that. We know better now on the software side.
Yeah, and also for the SOA, when we have C++ tricks could fall back to the AOS access way. Yeah, so for the old code can easily port it.
But these different build options, the legacy ones, they're going to get deleted. They're going to go away. So there'll only be one in future.
And what are exactly the structures you make into it?
Great. Any other questions? Next? Okay, we'll try and keep it a little bit on time. Thank you, Yang.